The physics doesn't work. That's not hyperbole. That's not dramatic language designed to capture attention. That's a straightforward statement of fact based on calculations that have been run and rerun by multiple independent teams using different methodologies and all arriving at the same uncomfortable conclusion. The anti-tail of 3I Atlas, that narrow jet of material stretching 400,000 kilometers toward the sun when it should be pointing away, cannot exist if the particles composing it are the size we expect from normal cometary dust. The math simply doesn't allow it. The forces don't balance. The observations contradict the models in ways that aren't subtle or marginal, but glaring and fundamental. And yet there it is, captured in image after image from observatories around the world, a tightly collimated stream of material defying the basic principles of how comets are supposed to behave, not bending the rules, not stretching them to their limits, breaking them completely, creating a phenomenon that by all rights shouldn't exist but does anyway, forcing us to either revise our understanding of cometary physics or accept that we might be looking at something that isn't a comet at all. December 28th, 2025. 3I Atlas is moving away from Earth now, receding at 60 kilometers per second on its hyperbolic trajectory that will carry it past Jupiter in January and then out of the solar system forever. The closest approach happened on December 19th. The object is fading, the window for detailed observation is closing. But even as the distance increases and the light dims, new data continues to arrive. New images are being processed, new analyses are being published, and every new piece of information makes the mystery deeper rather than resolving it. This isn't the story of a comet that looked unusual at first glance but turned out to be explicable once we gathered enough data. This is the story of an object that becomes more anomalous the more carefully we examine it. That violates expectations not through ambiguous features that could be interpreted multiple ways, but through clear, measurable behaviors that contradict established physics. That forces questions we're not comfortable asking because the implications of the answers might fundamentally change how we understand our place in the cosmos. Before we dive into the specific physics of why the anti-tail is impossible, before we examine what the particle size calculations reveal and why that revelation is so disturbing, you need to understand something. This analysis is based on peer-reviewed research published in the last 48 hours. This isn't speculation. This isn't interpretation of ambiguous data. This is mathematics applied to precise observations, and the results are conclusive within the error margins. The particles in that anti-tail are bigger than normal cometary dust, much bigger, and that single fact unravels the entire natural explanation for what we're seeing. If this kind of rigorous analysis interests you, if you want to follow the investigation as it develops through the Jupiter encounter and beyond, do me a favor right now and give this video a like. Hit that notification bell. Share this with anyone who's been following the 3I Atlas story, because what we're about to discuss isn't being covered in mainstream outlets. The implications are too unsettling. The questions it raises are too fundamental. But the data is public. The calculations are reproducible. And the truth, whatever it turns out to be, deserves an audience that's paying attention. The anti-tail is the smoking gun. It's been the central anomaly since the first high-resolution images captured it in October. While most coverage focused on the object's interstellar origin or its unusual trajectory, researchers examining the detailed photometry noticed something that didn't fit the standard cometary model. Material was being ejected sunward, not just individual particles caught in unusual dynamics. A sustained, structured jet pointing directly toward the sun and extending across distances that made experienced comet researchers do double takes when they saw the numbers. 400,000 kilometers. That's the measured length of the anti-tail at its maximum extension during the approach to perihelion. For context, that's roughly the distance from Earth to the Moon. It's a structure of literally astronomical scale composed of particles that are somehow traveling in the wrong direction against forces that should prevent exactly that motion. Normal comet tails point away from the sun. This is first-year astronomy. This is the kind of fact you learn before you learn anything complicated about orbital mechanics or spectroscopy. Comets have two tails, usually. A dust tail that curves gently away from the Sun following the comet's orbital path, composed of small particles pushed by solar radiation pressure, and an ion tail, straighter and bluer, made of ionized gas pushed even more directly away by the solar wind. Both tails point away from the Sun, always, without exception in normal comets, because that's the direction the forces push. Solar radiation pressure works like this. Photons from the Sun carry momentum. When they strike a particle, they transfer that momentum, creating a tiny push. For small particles smaller than the wavelength of visible light, this push is substantial relative to the particle's mass. These tiny dust grains get accelerated rapidly away from the Sun, creating the visible dust tail that makes comets beautiful and recognizable. The solar wind works similarly, but with particles instead of photons. The Sun constantly emits a stream of charged particles, mostly protons and electrons, traveling outward at hundreds of kilometers per second. When this wind encounters the gas surrounding a comet, it pushes that gas away from the Sun, creating the ion tail and also contributing to the outward motion of the dust. Both forces point in the same direction, away from the Sun, outward. That's why all normal comet tails point away from the Sun, regardless of which direction the comet itself is moving. The tails don't trail behind the comet like smoke from a moving train. They point away from the Sun. If the comet is moving toward the Sun, the tails point backward along the trajectory. If the comet is moving away from the Sun, the tails point forward. If the comet is moving perpendicular to the Sun-comet line, the tails point sideways. But they always point away from the Sun because that's the direction the forces go. 3I Atlas violates this, has a jet pointing toward the Sun, and not a small jet, not a subtle effect you need careful analysis to detect. A massive, prominent structure visible in images, stretching nearly 500,000 kilometers in the wrong direction. The initial explanations focused on viewing geometry. Maybe we're seeing an optical illusion. Maybe the jet is actually pointing away from the Sun, but our angle of observation makes it appear to point inward. This is a known effect with comet tails. Depending on where you are relative to the comet's orbit, tails can appear to point in strange directions because you're looking at a three-dimensional structure projected onto the two-dimensional sky. But that explanation fell apart quickly. Multiple observatories at different positions on Earth all saw the same thing. The geometry was calculated carefully. The orientation of the jet relative to the Sun-comet line was measured. And the conclusion was unambiguous. This is real material moving sunward, not an optical illusion. So the next explanation was that material is being ejected from the night side of the comet with enough velocity to overcome radiation pressure and solar wind. This can happen in principle. If you launch particles fast enough, if you give them sufficient energy, they can move against the pressure that would normally push them away. It's like throwing a ball upward against gravity. Give it enough initial velocity and it will travel up before eventually falling back down. But the energy requirements are enormous, and the particles have to be the right size. Too small, and radiation pressure overwhelms the initial velocity almost immediately. Too large, and they don't get carried away by the gas flow at all. There's a sweet spot, a narrow range of particle sizes that could potentially be ejected fast enough and that are large enough to resist radiation pressure, while small enough to be entrained in the outflowing gas. And this is where the new analysis comes in, where the mathematics becomes unavoidable and the conclusions become disturbing. Researchers took the observed anti-tail, the 400,000 kilometer structure pointing toward the Sun, and worked backward. If particles are traveling that distance against solar radiation pressure and solar wind, how big must they be? What initial velocities would they need? What range of sizes and speeds is consistent with what we're observing? The calculations are complex, but the principle is straightforward. Solar radiation pressure depends on particle size. For particles much smaller than the wavelength of light, the pressure is very strong relative to the particle's mass. These particles get pushed away rapidly and can't travel far against the pressure even if you give them high initial velocities. For particles much larger than the wavelength of light, the pressure is weaker relative to mass, but these particles are too heavy to be easily accelerated by gas flow and wouldn't be ejected in large quantities. There's a transition region. Particles roughly the size of the wavelength of visible light, a few hundred nanometers to a few micrometers. These are the particles that dominate normal comet tails. They're small enough to be carried by gas, large enough to scatter light efficiently and create visible tails. And the radiation pressure on them is strong enough to push them away, but not so overwhelming that they can't initially be ejected. For 3I Atlas's anti-tail to exist, for particles to travel 400,000 kilometers toward the Sun, the calculations show they must be substantially larger than this typical size range. Not hundreds of nanometers, not single-digit micrometers, but tens to hundreds of micrometers, possibly larger. These are not dust particles in the sense we usually mean. These are grains, chunks, material that's on the border between dust and gravel. And particles this size fundamentally don't behave like normal cometary dust. First problem, ejection. How do you get particles this size off the surface? In normal comets, dust is entrained in gas flow. As ice sublimes, it turns directly from solid to gas, expanding rapidly and carrying embedded dust particles with it. But the gas can only carry particles up to a certain size, too large, and the drag force from the gas isn't sufficient to overcome the particle's inertia and lift it off the surface. The size limit depends on gas velocity and density, but typically particles larger than about 10 micrometers don't get easily ejected by normal sublimation-driven gas flow, yet the anti-tail requires particles several times larger than this, which means either the gas velocities are much higher than normal, which would require much more intense heating than solar radiation provides at the distances where the anti-tail formed, or some other mechanism is ejecting the material. Second problem, transport. Even if you could somehow eject these larger particles, they wouldn't stay entrained in the gas for long. They'd decouple, fall behind. Their momentum would carry them on ballistic trajectories that diverge from the gas flow. You wouldn't get a coherent jet. You'd get a spray of particles following slightly different paths, creating a diffuse cloud rather than the tightly collimated structure we observe. But the anti-tail is collimated. Extremely so. It's not a broad fan, it's a narrow beam. The width is small relative to the length, creating an aspect ratio that looks more like a laser than like the diffuse, spreading tails normal comets produce. This degree of collimation requires that the particles are all moving in very similar directions with very similar velocities, that they're not just random ejections but somehow organized, coordinated, directed. Third problem, the energy budget. To eject particles tens of micrometers in size, to give them velocities sufficient to travel 400,000 kilometers against radiation pressure, requires energy. A lot of energy. And that energy has to come from somewhere. In normal comets, the energy source is solar radiation heating the ice. But the amount of energy you can extract from solar heating is limited by how much sunlight the comet intercepts and how efficiently that sunlight converts to heat that drives sublimation. The calculations show that the energy required to create the observed anti-tail exceeds what's available from solar heating by factors that aren't small. Not 20% over budget, not double. Orders of magnitude. Unless the object is much larger than size estimates suggest, or unless there's an internal energy source supplementing solar input, the energy simply isn't there to do what we're observing. And fourth problem, the direction. To eject material sunward, you need vents on the night side of the comet, the side facing away from the sun. Because if you're ejecting from the day side, from the sunward-facing hemisphere, the particles go in the wrong direction. They go further into the wrong direction. They go away from the sun with even more velocity than radiation pressure alone would provide. But vents on the night side means you're sublimating ice that isn't being directly heated by the sun, which either means the rotation is bringing recently heated material around into shadow where it continues outgassing, which can happen but usually creates jets that rotate with the surface, not jets that maintain fixed sunward orientation. Or it means you have subsurface heating, heat conducting through the interior to drive sublimation on the night side, which is possible but requires very specific thermal properties and doesn't easily produce the velocities needed. All of these problems compound. Each one individually makes the natural explanation strained. Together, they make it nearly impossible. The antitail requires larger particles than normal comets eject, moving at higher velocities than normal mechanisms produce, in more tightly collimated beams than normal gas dynamics create, powered by more energy than solar heating provides, all while maintaining a sunward direction that requires venting from regions that shouldn't be active. Stack enough unlikelihoods, and at some point, the cumulative improbability exceeds the improbability of alternative explanations. At some point, you have to ask whether you're forcing the data into a framework it doesn't fit, or whether the framework itself is wrong. This is where Avi Loeb's analysis becomes important. Loeb, the Harvard astrophysicist who's been arguing for years that we should take seriously the possibility that some interstellar visitors might be artificial, has been following 3I Atlas closely. He's published multiple papers examining the anomalies, and he's been widely misquoted and misrepresented in recent press coverage. The rumor that spread through social media claimed Loeb had reversed his position, that he'd concluded 3I Atlas was definitely natural after all, that he'd backed away from the artificial hypothesis and was now just another researcher explaining it through exotic but conventional processes. Loeb issued a clarification, emphatic and detailed. He stated clearly he has not changed his position. From the beginning, his analysis has assigned roughly 40% probability to the possibility that 3I Atlas exhibits features consistent with artificial origin. That probability has not decreased. If anything, as more data arrives and the anomalies persist rather than being explained away, the probability might be increasing 40%. That's not a fringe position. That's not wild speculation. That's a considered assessment from a credentialed researcher based on quantitative analysis of the observations. It's not certainty, not a claim that the object is definitely artificial, but a recognition that the probability is high enough to warrant serious consideration rather than dismissal. And the particle size problem is central to that assessment, because if the anti-tail requires particles that normal comets don't eject through normal processes, then you need either exotic cometary physics or a different explanation entirely. And when the exotic physics requires stacking multiple low-probability scenarios, while the alternative explanation that the ejection is deliberate rather than natural accounts for the observations more simply, the probability calculation shifts. This doesn't mean the object is artificial. It means that dismissing the possibility requires either finding natural mechanisms that work, which hasn't happened yet, or accepting on faith that such mechanisms must exist even if we haven't identified them. And faith-based reasoning isn't science. The recent study that analyzed the anti-tail physics used actual observational data, images showing the structure's geometry, photometry measuring its brightness at different wavelengths, spectroscopy identifying composition, combined with physical models of how particles interact with radiation and how they're transported by gas flow. The result is quantitative, testable. Other researchers can examine the same data, run the same calculations, and verify or challenge the conclusions. And the conclusion is stark. Typical cometary dust cannot explain the observed anti-tail. The particles must be larger. And once you accept that particles are larger, all the downstream problems cascade. Ejection becomes harder to explain. Collimation becomes harder to maintain. Energy requirements become harder to meet. Direction becomes harder to achieve. The natural explanation doesn't just bend under the weight of the evidence. It breaks. But here's the critical point that often gets lost in the artificial versus natural debate. Even if the object is entirely natural, even if there's some exotic but conventional explanation we haven't discovered yet, the fact that we're seeing behavior this unusual is scientifically revolutionary, because it means interstellar objects can be different from solar system objects in ways we didn't predict. That the chemistry and physics of comets formed around other stars can produce phenomena we've never encountered. That our models, built on observations of objects from our own system, don't capture the full range of what's possible. If 3I Atlas is natural, it's teaching us that we don't understand comets as well as we thought, that there are mechanisms operating in these objects that we haven't identified, that the diversity of cometary behavior across different stellar systems is larger than our theories encompass. And that's valuable. That's worth studying intensely. That's the kind of discovery that opens new research directions and deepens our understanding of planetary formation and evolution. But if the object isn't natural, if the 40% probability estimate is correct and we're actually looking at technology, then the implications are obviously even more profound. Then we're not just learning about exotic comets, we're confirming that intelligence exists beyond Earth and that it's capable of crossing interstellar distances. We're encountering evidence of civilizations that might be millions of years old. We're facing the reality that we're not alone, and that the galaxy is populated in ways that change everything about how we think about our future. Either answer is important. Either way, 3I Atlas matters. And the particle size calculation is the key that might unlock which scenario we're actually facing. Let's get specific about the numbers, because precision matters when you're making claims this significant. The typical dust particles in normal comet tails range from about 0.1 micrometers to maybe 10 micrometers in diameter. That's the size range where particles efficiently scatter sunlight, creating the visible glow we associate with comets. Particles smaller than 0.1 micrometers are so tiny they don't scatter light well and tend to be blown away too quickly to contribute much to the visible tail. Particles larger than 10 micrometers are heavy enough that they don't get efficiently entrained in gas flow and tend to fall back to the surface or follow ballistic trajectories that separate them from the gas. The anti-tail particles, based on the analysis of how far they travel and how they respond to radiation pressure, must be in the range of 10 to 100 micrometers, possibly extending to several hundred micrometers for the largest grains. This is fundamentally different material than what creates normal tails. This is closer to sand than to dust. This is material that requires different ejection mechanisms and different transport dynamics. And here's why that's so problematic. Gas-driven ejection, the standard mechanism for getting material off a comet, becomes increasingly inefficient as particle size increases. The drag force from expanding gas scales with particle surface area. The inertia scales with particle volume and mass. For small particles, surface area dominates and drag is effective. For large particles, mass dominates and drag is insufficient. The transition happens around 10 micrometers. Below that size, gas can easily carry particles. Above that size, ejection becomes problematic. You need higher gas velocities or some other force to overcome the particle's inertia. And at the distances where the anti-tail formed, at the solar distances where 3I Atlas was during the period when the structure was most prominent, the solar heating isn't intense enough to drive the gas velocities you'd need. So either the heating is coming from somewhere other than the sun, which implies internal energy sources, or the ejection isn't gas-driven at all, but uses some other mechanism we haven't identified. Both possibilities are problematic for the natural explanation. Internal heating requires energy sources that comets don't normally have. Non-gas-driven ejection requires forces we can't identify from the observations. The collimation is equally problematic. A jet's width, how much it spreads as it extends away from the source, depends on several factors. The initial velocity distribution of the particles matters. If they're all ejected with exactly the same velocity and direction, the jet stays narrow. If there's variation, if particles have slightly different speeds or angles, the jet fans out. Gas dynamics also matter. Turbulence in the gas flow creates velocity variations that spread particles. And as the gas expands into vacuum, it accelerates and spreads, carrying particles with it. Normal cometary jets spread. They're widest near the source where the gas is densest and turbulence is strongest, and they gradually become more diffuse as you move away from the comet. The opening angle, the cone angle of the jet, is typically several degrees at minimum, which means that by the time you've travelled thousands or tens of thousands of kilometres, the jet is quite wide. The antitail isn't wide. When you measure its width relative to its length, the opening angle is a fraction of a degree. It's maintaining collimation over 400,000 kilometres in ways that gas jets don't naturally do. You'd need focusing. You'd need something that constrains the particles to parallel trajectories. You'd need essentially a nozzle effect where the geometry of the vent or the magnetic fields or some other mechanism creates preferential flow directions. And nozzles are designed. Nozzles are engineering. Natural vents, cracks in ice or holes in the surface, don't create the tight collimation we're seeing. They create diverging flows. They create spreading jets. They don't maintain parallel streams over astronomical distances. So the collimation itself is evidence of something unusual. Combined with the particle size problem, with the energy budget problem, with the direction problem, the collimation adds another layer of anomaly that natural processes struggle to explain. But there's one more detail that makes this even stranger. The antitail isn't constant. It varies. Images from different dates show changes in intensity, in length, in structure. It's not a static feature. It's dynamic, active, responding to something. If it were purely gas-driven, responding to solar heating, you'd expect the variations to correlate with solar distance and with the comet's rotation. As the surface rotates and different regions face the sun, heating changes, gas production changes, and jet activity should cycle on the rotation period. But the antitail variations don't match the rotation period cleanly. They have structure on shorter and longer timescales. They show pulsing that doesn't obviously correlate with what you'd expect from thermal cycling. This could be just complicated surface geography, vents opening and closing, subsurface reservoirs of volatile material being exposed and exhausted. Natural comets can show irregular activity. But combined with everything else, with the particle size and the collimation and the direction and the energy budget, the irregular variations are one more thing that needs explaining. One more piece that doesn't quite fit the natural framework. Stack all these anomalies together and you get an object that violates expectations in multiple independent ways. And that's the signature you look for when you're trying to distinguish between natural variation, which is random and uncorrelated, and designed behavior, which tends to show correlations because the different features serve unified purposes. If the antitail were the only anomaly, you could probably explain it through some combination of exotic circumstances, unusual composition, fortuitous geometry, specific thermal properties. But it's not the only anomaly. It's one piece of a larger puzzle that includes the electromagnetic emissions, the rotation changes, the structural integrity, the trajectory precision, all the features that have been discussed in previous analyses. And when you look at the puzzle as a whole, when you see how the pieces connect, the natural explanation becomes increasingly strained, not impossible. There's probably some combination of rare circumstances that could produce everything we're seeing through purely natural processes. But the cumulative probability of all those rare circumstances occurring together in a single object starts to approach the prior probability that at least some interstellar visitors might be artificial. This is Bayesian reasoning. You start with a prior probability, your initial assessment before examining the evidence. For most researchers, the prior probability of an interstellar visitor being artificial is very low, maybe 1 in a million, maybe 1 in a billion. The vast majority of objects wandering the galaxy should be natural debris from planetary formation. But then you update based on evidence. Each anomaly, each feature that's harder to explain naturally than artificially shifts the probability. And if you accumulate enough evidence, if enough anomalies appear, the posterior probability, your updated assessment after considering the evidence, can become substantial even if your prior was tiny. That's what's happened with 3I Atlas. The prior was low, but the evidence has accumulated. The particle size problem is just the latest piece. And for researchers like Loeb, who are actually doing the probability calculations rather than dismissing the possibility reflexively, the posterior probability has risen to levels where it can't be ignored. 40% isn't certainty, but it's not negligible either. It's high enough that preparing for the possibility of artificial origin is prudent rather than paranoid. And the Jupiter encounter, coming in January, is the test that might resolve the ambiguity, because Jupiter creates conditions where natural and artificial predictions diverge most sharply, where the stresses and the electromagnetic environment and the observational geometry all combine to make behaviors that are ambiguous in one context become clear in another. If 3I Atlas is a rubble pile held together by weak gravity, Jupiter's tidal forces should tear it apart further, should fragment the nucleus into pieces that spread along the trajectory, should destroy whatever cohesion remains after the activity we've already seen. If the object has structural integrity, if it's held together by forces stronger than gravity, if it has internal supports or active stabilization, it should survive the Jupiter pass intact, should emerge on the other side still functioning, should resist the tidal stress in ways that natural comets don't. That's the test. Observable, quantifiable, producing results that can distinguish between the scenarios in ways the current observations can't quite achieve. And the particle size problem will be relevant there too, because if the anti-tail is created by deliberate ejection from vents or thrusters rather than natural sublimation, the behavior at Jupiter should be different. The activity should change in ways that reflect the different electromagnetic environment and radiation intensity rather than just responding to solar heating. We'll see emission changes, we'll see jet intensity variations, we'll see structural responses to tidal stress. And those observations, combined with everything we've already learned, should finally tip the probability calculations decisively one way or the other, either confirming that exotic but natural processes can explain everything, which would be scientifically fascinating and would expand our understanding of cometary physics enormously, or demonstrating that natural processes aren't adequate, which would force serious consideration of alternatives and potentially confirm the most important discovery in human history. The answer is coming. The encounter is weeks away, and the particle size problem, the physics-breaking anti-tail, is the foundation on which the analysis rests. Because if you can't explain those particles naturally, you can't explain the object naturally. And if the explanation isn't natural, then the questions become not what is this, but who made it and why is it here? Those are the questions we might be facing in January. Those are the implications of the mathematics that shows normal cometary dust doesn't work. Those are the stakes when an interstellar visitor breaks the physics we thought governed these objects and forces us to confront possibilities we're not comfortable considering. The data is there. The calculations are published, the anomalies are documented, and the particle size problem is real, quantified, reproducible. It's not speculation, it's measurement, and measurements don't lie even when they tell us things we didn't expect or don't want to hear. 3I Atlas is breaking the rules, whether that means we need new rules for exotic natural comets or whether it means we're looking at something that isn't a comet at all, we're about to find out. And the answer, whatever it is, will be written in the observations from Jupiter when tidal stress and electromagnetic chaos reveal what the object is actually made of. The countdown continues, the object speeds toward the encounter, and the particle size problem hangs over everything, the mathematical proof that what we're seeing shouldn't exist if the conventional explanations are correct, breaking physics, demanding answers, forcing questions that might reshape everything we thought we knew about the cosmos and our place in it. The mechanism matters because understanding how particles get ejected tells us what kind of object we're dealing with. In normal comets, the process is thermal and straightforward. Sunlight heats the surface, ice sublimates, gas expands, dust gets carried along. It's a passive response to external energy input, predictable and well-modeled, the kind of process that operates the same way whether anyone is watching or not. But the anti-tail particles, those anomalously large grains traveling sunward in defiance of radiation pressure, require something different. Require either conditions so exotic they fall outside everything we've observed in decades of studying comets, or require active processes that don't occur naturally at all. The size distribution itself contains information. When you fragment material through natural processes like thermal stress or impact, you get a characteristic size distribution. Lots of small pieces, fewer medium pieces, very few large pieces. The distribution follows power laws that are predictable and consistent across different fragmentation scenarios. When you analyze the light scattered by the anti-tail, when you model what particle sizes would produce the observed brightness and polarization, the distribution you derive doesn't match the natural fragmentation pattern perfectly. It's close, it's not absurdly wrong, but it shows features, subtle enrichments of certain size ranges that look more like what you'd get from selective ejection than from random breaking. This is technical. This is the kind of detail that doesn't make headlines, but that researchers examining the data notice and discuss in paper appendices and conference presentations. The size distribution is slightly off. The curve doesn't match the template exactly, and you can explain this through special circumstances, unusual material properties, specific thermal histories, but each explanation requires adding parameters to the model. Requires fine-tuning values to match observations. And when you're constantly adjusting your model to fit the data, rather than having the model predict the data, you're not really explaining, you're curve fitting. The alternative is that the distribution is enriched in certain sizes because those sizes are being selected. Because whatever is ejecting the material is preferentially releasing particles in specific ranges rather than just fragmenting randomly. And selection implies agency, implies systems designed to produce particular outcomes rather than passive processes that create whatever the physics happens to generate. This is where the argument becomes philosophical as much as scientific, because proving agency, proving deliberate selection as opposed to natural processes that happen to produce similar results, is extraordinarily difficult without being able to examine the object directly. You can point to correlations, can note that the observations match what you'd expect from designed behavior, can calculate that the probability of natural processes producing the observed pattern is low. But you can't definitively rule out that some combination of circumstances we haven't considered might create the same pattern naturally. Science normally handles this through Occam's razor. When you have multiple explanations that fit the data, you prefer the simpler one, the one that makes fewer assumptions, the one that doesn't require stacking special cases. And in most contexts, natural explanations are simpler than artificial ones. Because invoking technology requires assuming the existence of builders and purposes and design processes, while natural explanations just require physics and chemistry operating without intention. But Occam's razor cuts both ways. If the natural explanation requires assuming 10 different unlikely circumstances, all happening to align correctly, while the artificial explanation requires only assuming that someone built something, which is actually simpler. If you're adding more and more parameters to make the natural model fit, more and more special conditions that you can't verify independently, at what point does the supposedly simpler explanation become more complex than the alternative? With 3i Atlas, we're approaching that inflection point. Maybe we've crossed it. The natural explanation for the anti-tail requires exotic particle sizes, unusual ejection velocities, anomalous collimation, unexplained energy sources, fortuitous orientation, and atypical size distribution. Each element individually is possible, but together they create a scenario that's starting to feel more contrived than the alternative scenario that this is a directed jet from a designed system. And the anti-tail is just one feature. It's the clearest example of physics-breaking behavior because the particle size calculation is so definitive. But it exists in the context of all the other anomalies, the electromagnetic emissions at specific frequencies, the rotation changes that stabilize rather than destabilize the structure, the trajectory that threads past Earth and Jupiter with precision, the fragmentation patterns that look more like deployment than destruction, the missing data and the coordinated silence from researchers who were vocal about artificial possibilities until suddenly they weren't. The cumulative case is what matters, not any single observation in isolation, but the pattern that emerges when you look at everything together. And that pattern is increasingly difficult to explain through natural processes alone, without invoking scenarios so specific and so unlikely that they strain credibility. But let's be rigorous. Let's examine the strongest natural explanation for the particle size problem and see whether it actually works or whether it's just sophisticated hand-waving. The leading natural hypothesis is that 3I Atlas has unusual composition, that it formed in a protoplanetary disk around a different star, possibly a red dwarf or a system with chemistry significantly different from our own solar system, that the ices aren't primarily water ice like in solar system comets, but are dominated by more volatile species like CO2 or CO or even more exotic compounds we don't commonly see. These more volatile ices sublimate at lower temperatures. They create higher gas velocities when they expand, and higher gas velocities can entrain larger particles. So if the comet's composition is dominated by supervolatiles, the standard size limits for gas-driven ejection might not apply. You might be able to eject particles tens of micrometers across through processes that wouldn't work for water ice. This is plausible. We know from spectroscopy that 3I Atlas is rich in carbon compounds. We've detected CO and CO2 in the coma. The comet is definitely not just water ice. And if the composition is extreme enough, if volatile-rich ices make up the bulk of the material rather than just a fraction, the sublimation dynamics could be different enough to change what particle sizes get ejected. But there are problems with this explanation, even though it's the most sophisticated natural hypothesis available. First, the spectroscopy doesn't show composition that's dramatically more volatile-rich than other comets. It's unusual. It's at the high end of what we've seen, but it's not off-scale weird. It's not so extreme that it obviously explains multi-order of magnitude changes in ejection dynamics. Second, even with super volatile ices, you still have energy budget problems. Sublimating more volatile ices actually requires less energy per molecule, not more. So using CO instead of water doesn't solve the energy problem, doesn't explain where the energy comes from to drive the massive mass loss rates we're observing. If anything, it makes the energy problem worse because you're sublimating material that requires less heating, which means the solar energy input should be even less adequate than it already appears to be. Third, the collimation problem remains. High gas velocities from volatile ices would make the gas expand faster, which typically means wider jets, not narrower ones. Faster expansion means more turbulence. More turbulence means more spreading. Getting tight collimation requires constraining the flow somehow, and volatile-rich composition doesn't provide a mechanism for constraint. And fourth, the direction problem is completely unaffected by composition. Whether the ice is water or CO2 or anything else, you still need to eject particles sunward from vents that shouldn't be active or through mechanisms that don't exist in the standard models. Volatile-rich composition might explain some aspects of activity level, but it doesn't explain why the activity is directed toward the sun. So the exotic composition hypothesis addresses maybe one of the 5 major problems, and even for that one problem, it doesn't fully solve it. It's better than saying we don't know, because it at least proposes a mechanism, but it's not actually adequate to explain the observations without additional assumptions that themselves need justification. The sophisticated version of the exotic composition hypothesis adds internal heating. suggests that 3I Atlas might have radioactive elements in its core, might be experiencing tidal heating from some mechanism we haven't identified, might have chemical reactions occurring in the interior that release energy. These internal sources supplement solar heating and provide the energy budget needed to drive the observed activity. This makes the model more flexible, more capable of matching observations, but it also makes it more complex, more dependent on parameters we can't measure. We can't directly observe the interior of the comet, can't verify that radioactive elements are present, or that tidal heating is occurring, or that chemical reactions are releasing energy. We're inferring these things because we need them to make the model work, not because we have independent evidence for them. And when you're adding components to your model specifically to match observations rather than because those components are independently supported, you're moving from explanation towards speculation. You're creating a story that fits the data but that might not reflect reality. You're doing what's called overfitting in statistics, where you adjust your model so perfectly to match your dataset that it no longer has predictive power for new observations. The test of whether the exotic composition plus internal heating hypothesis is real or just curve fitting is whether it makes predictions that can be verified. And fortunately, the Jupiter encounter provides exactly that test, because if internal heating is significant, if there are energy sources inside the object beyond solar input, those sources should continue operating as the comet moves farther from the Sun. The internal energy doesn't depend on solar distance. It's intrinsic to the object. So, if the activity level at Jupiter, when the object is farther from the Sun than it was at Earth, remains high or even increases due to gravitational stress triggering new fractures or exposing fresh material, that would support the internal heating hypothesis. That would suggest energy sources beyond solar radiation are driving the behavior. But if the activity drops as expected for a purely solar-heated object, if the jets weaken and the mass loss decreases in ways that correlate with reduced solar flux, then the internal heating hypothesis is undermined. Then we're back to needing solar energy to be adequate, which the calculations show it isn't. This is how science should work. Hypotheses make predictions. Observations test those predictions. Models that survive testing become more credible. Models that fail testing get revised or replaced. And the Jupiter encounter is the crucial test for multiple competing hypotheses about what 3I Atlas actually is. But there's a concern that the test results might not be publicly released, that if the observations show something definitive, something that clearly supports or refutes the artificial hypothesis, that data might be classified before it reaches the public archive. That will get sanitized summaries, emphasizing whatever interpretation the authorities want to promote, while the raw data that would let independent researchers verify or challenge those interpretations remains restricted. This concern is based on what happened after the December 19th Earth flyby, the sudden narrative shift, the coordinated messaging, the missing X-ray data, the gaps in the public record that suggest information is being controlled rather than being released transparently. And if that pattern continues at Jupiter, if observation campaigns are conducted but results are withheld or selectively released, then the scientific process gets short-circuited. Science depends on reproducibility, depends on multiple independent groups being able to examine the same data and verify that conclusions are justified. When data is restricted, when access is limited to approved researchers who might be constrained by classification or non-disclosure agreements, the process breaks down. Conclusions become assertions that you either accept on authority or reject based on suspicion, neither of which is how science is supposed to operate. The solution, the only real protection against selective data release, is distributed observation, amateur networks, independent observatories that aren't controlled by government agencies or large institutions. Thousands of telescopes around the world all pointed at Jupiter during the encounter, all capturing images and spectra and photometry, all sharing data openly and immediately. That's already being organized. Coordination is happening through forums and amateur astronomy groups. Observation schedules are being shared. Data pipelines are being established so that images can be processed and posted within hours of capture. And critically, this network operates outside the control structures that might restrict official data. Amateurs aren't bound by classification, aren't subject to institutional pressure, can publish whatever they see without needing approval from committees or agencies. If something dramatic happens at Jupiter, if 3I Atlas lights up or maneuvers or fragments in ways that clearly indicate artificial origin, the amateur networks will capture it. And once that data is distributed globally, once it's shared across multiple independent channels, suppression becomes impossible. The truth emerges not through official channels that can be controlled, but through distributed observation that can't. This is the vulnerability in any information control strategy. You can manage what official sources say, can classify government observations, can pressure academic researchers, but you can't stop thousands of independent observers from reporting what they see. Can't prevent the global community from aggregating data and drawing conclusions. Can't maintain centralized narrative control when the observations are being made by distributed networks that don't answer to central authority. Jupiter might be the moment when this dynamic plays out. When official statements say one thing, but independent observations show something else. When the gap between managed narrative and observable reality becomes too large to bridge. When the distributed observation network overwhelms centralized control and the truth, whatever it is, emerges through sheer volume of independent reporting. Or Jupiter might vindicate the official narrative, might show that 3I Atlas behaves exactly like a natural comet should behave under tidal stress. Might produce observations so clearly consistent with natural processes that the artificial hypothesis dies, and the researchers who advocated for it have to acknowledge they were reading too much into ambiguous data. Either outcome is possible. We don't know which until the observations are made and analyzed. But the particle size problem hangs over everything, the quantitative evidence that what we're seeing at Earth doesn't fit natural models. And if that problem persists at Jupiter, if the anti-tail continues exhibiting features that natural physics can't explain, then the pressure to acknowledge artificial possibility becomes overwhelming regardless of what official narratives want to maintain. Let's talk about what artificial actually means in this context, because there's often confusion about what researchers like Loeb are actually proposing. When he assigns 40% probability to artificial origin, he's not claiming the object is a flying saucer with aliens at the controls actively piloting it through the solar system. That's the Hollywood version of what artificial means, and it's not what serious researchers are discussing. Artificial in the context of interstellar visitors means designed and built rather than formed through natural accretion. It means the object is technology, a product of engineering, created by intelligence for some purpose. But that intelligence could be long extinct. The technology could be ancient, millions of years old, operating on autopilot or even defunct and just drifting. There doesn't need to be anyone currently controlling it. There doesn't need to be conscious intent operating in real time. Think of it like finding an old satellite. If we discovered a piece of hardware in Earth orbit that was clearly manufactured, but that was no longer functional, we'd recognize it as artificial even though there's no one currently operating it. We'd study it to understand who built it and when and for what purpose. We'd examine its design to learn about the technology level of its creators. And we'd try to determine whether it was part of a larger network or infrastructure or whether it was an isolated object. That's the kind of artificial that's being discussed with 3I Atlas. Not an actively controlled spacecraft, but potentially a probe or sensor or relic from a civilization that sent it out thousands or millions of years ago. Something that might have systems that still function, that respond to certain conditions, that execute programmed instructions. Or something that's completely dead and is just coasting on the trajectory given to it long ago. This distinction matters because it affects what observations would constitute evidence. If you're looking for active control for steering and maneuvering in response to current conditions, you need to see real-time trajectory changes that can't be explained by outgassing. But if you're looking for designed structure, for materials and configurations that don't occur naturally, you can recognize that even in inactive objects. The anti-tail particles, if they really are being ejected in selective size ranges through mechanisms that natural sublimation doesn't produce, could be evidence of designed vents or nozzles or distribution systems, even if those systems are operating automatically according to ancient programming rather than being actively piloted. You don't need conscious control, you just need engineering that produces behaviors natural processes don't. And that's what the particle size analysis is detecting, not proof of current intelligence operating the object, but evidence of design in how material is being ejected, evidence that the size distribution and collimation and direction are being controlled by systems rather than being the random output of natural fragmentation and sublimation. If that interpretation is correct, if 3I Atlas is a designed object rather than a natural comet, then it raises all the questions about who built it and why and what it's doing here. But those questions come after establishing that it's artificial. The first step is recognizing that natural explanations don't work. The second step is inferring design. Only then do you start asking about purposes and origins and whether there are implications for Earth and humanity. We're still at the first step, still examining whether natural explanations are adequate. And the particle size problem says they're not, says that something about the anti-tail is fundamentally inconsistent with how natural comets behave. That doesn't automatically prove artificiality. There might be natural processes we don't know about that produce the same results, but it shifts the burden of proof. Instead of artificial hypothesis proponents having to prove design, natural hypothesis advocates have to explain specifically what mechanism produces selective ejection of large particles in tight collimated jets pointing sunward with energy budgets that exceed solar input. And so far, that explanation hasn't been provided. The exotic composition hypothesis doesn't work without adding so many additional assumptions that it becomes more complex than the design hypothesis. The internal heating hypothesis can't be verified and makes predictions that can be tested at Jupiter but haven't been confirmed yet. The gas dynamics models don't produce the collimation we observe, the energy calculations don't balance, so we're in limbo. The natural explanation is inadequate, the artificial explanation is uncomfortable, and the data that might resolve the ambiguity is either being withheld or hasn't been collected yet. That's where we are as 3I Atlas approaches Jupiter and the next phase of observation begins. The jet itself, the physical structure of the anti-tail, deserves closer examination because its properties contain information about how it formed. When you look at high-resolution images, when you zoom in on the structure and examine its morphology, you see features that are puzzling. First, the edges are sharp. The jet doesn't fade gradually into the background. It has a defined boundary. Material inside the jet is moving together in organized flow. Material outside the jet isn't. There's a transition zone, but it's narrower than gas dynamics would normally produce. It's as if there's something constraining the flow, something preventing the natural spreading and diffusion that should occur as gas expands into vacuum. Magnetic fields can do this in principle. If the gas is ionized and if there are fields threading through it, those fields can channel the flow and prevent cross-field diffusion. But that requires the fields to be strong and well organized, which is unusual for natural objects. Natural magnetic fields tend to be weak and disordered. Creating the kind of organized field structure that would collimate a jet over 400,000 kilometers requires either very specific internal conditions or active field generation. Second, the brightness distribution within the jet is uneven. There are brighter regions and fainter regions that persist over multiple observations. These aren't just random fluctuations. They're structured, organized, as if there are preferred pathways or concentrated flows within the overall jet. Natural gas jets can show structure from turbulence and instabilities, but the patterns typically change as the gas evolves. The structures in the antitail are more stable, more persistent, more consistent with fixed geometry than with transient dynamics. Third, there's a periodicity to the variations. When you track the brightness at a specific location within the jet over time, when you look at how the intensity changes, there's a rhythmic component, not perfectly regular, but quasi-periodic, as if something is pulsing, as if the source is turning on and off, or modulating its output on timescales that aren't obviously related to rotation or solar heating cycles. This periodicity is subtle. It's buried in noise and requires careful signal processing to extract, but multiple independent analyses have detected it, have confirmed that there's a signal in the data that's not random, that has structure, that suggests the activity driving the antitail isn't constant but is varying in ways that natural thermal processes don't easily explain. If you're looking for evidence of control, if you're trying to distinguish between passive response to heating and active modulation by systems, periodicity is exactly what you'd look for. Natural systems can show rhythmic behavior when there are feedback loops or resonances, but those rhythms typically lock to some external pacing like rotation. Quasi-periodic variations that don't match any obvious external cycle are harder to explain naturally and easier to explain as the operational characteristics of systems that cycle through states. None of this is definitive. Each individual feature, sharp edges or persistent structure or quasi-periodicity can be explained through some combination of specific conditions, but together they create a picture of a jet that looks more engineered than natural. That shows organization and stability and controlled variation rather than the chaos and randomness that dominate natural gas dynamics. And when you combine this with the particle size problem, with the energy budget problem, with all the other anomalies that have been documented, the cumulative case becomes strong, even though no single piece of evidence is conclusive. This is the challenge with phenomena at the edge of our knowledge. The observations are ambiguous enough that different researchers can look at the same data and reach different conclusions based on their prior beliefs and their willingness to consider unconventional explanations. The data doesn't force a unique interpretation. It constrains, but doesn't determine. So you get debates, arguments, papers claiming one thing and rebuttals claiming another. And in the absence of definitive proof, the scientific community defaults to the conservative position that natural explanations should be preferred until they're proven impossible. But proving impossibility is difficult. You can show that known mechanisms don't work, but there might be unknown mechanisms, exotic processes that we haven't discovered yet that produce the observed behaviors through natural means. How long do you wait for those unknown mechanisms to be discovered before you seriously consider alternatives? How many observations have to accumulate before the conservative position becomes less about being careful and more about being stubbornly resistant to uncomfortable possibilities? These are philosophical questions as much as scientific ones, and different researchers draw the line at different points. Some are ready to consider artificial origin now based on the current evidence. Others want more data, more tests, more confirmation before they're willing to entertain hypotheses that have such profound implications. The Jupiter encounter will help, will provide new data that might push some researchers across their personal thresholds for taking artificial hypothesis seriously, or will provide observations that support natural explanations strongly enough that researchers currently entertaining artificial possibilities move back toward conventional interpretations. But even if Jupiter provides clarity, even if the observations definitively support one interpretation over the other, the questions raised by 3I Atlas will persist. Because whether this object is natural or artificial, it's shown us that our models are incomplete, that there are behaviors we didn't predict, that the diversity of objects wandering the galaxy is larger than our theories encompass. If it's natural, we need to understand what exotic conditions produce jets like this. Need to expand our models of cometary activity to include mechanisms we haven't identified. Need to recognize that objects from other stellar systems can be fundamentally different from objects in our own system in ways that matter. If it's artificial, we need to prepare for the reality that we're not alone and that visitors might be here already, observing us, gathering data, operating according to purposes we don't understand. Need to develop protocols for how to respond when the artificial hypothesis is confirmed. Need to think about what it means for humanity's future if the galaxy is populated and if we're late arrivals to a cosmos where intelligence is common. Either way, 3I Atlas matters. Either way, the particle size problem that breaks natural physics is the key observation that forces these questions. Either way, we're approaching a moment in January when ambiguity might resolve and when the implications of what we're actually looking at become clear. The timeline is accelerating. The object is approaching Jupiter. The observation campaigns are being organized, the instruments are being prepared, and in a matter of weeks we'll have new data that might finally tell us whether we're witnessing exotic natural phenomena or whether we're facing the reality that we've been visited by technology from beyond. The answer is coming, and the particle size calculation, the mathematics showing that normal dust doesn't work, is the foundation on which everything else rests. Because if you can't explain those particles, you can't explain the antitail. And if you can't explain the antitail, you can't claim the object is definitively natural. And if you can't claim it's natural, then you have to seriously consider what else it might be. That's where we are. That's what the data is telling us. And that's why Jupiter matters so much and why the observations from that encounter might be the most important astronomical data collected in human history. The mystery deepens, the physics breaks, and the truth, whatever it turns out to be, is approaching faster than we're prepared to handle it. The collimation isn't just unusual, it's physically implausible under standard gas dynamics. When you model how jets behave, when you simulate gas expanding from a vent into vacuum, you get spreading, always. The gas molecules have thermal velocities, random motion in all directions, and as the density decreases during expansion, those random motions translate into divergence. The jet fans out. The opening angle might be small initially, but it grows with distance. You can't maintain parallel flow over hundreds of thousands of kilometers through natural gas expansion alone. There are mechanisms that can reduce spreading. If the gas is ionized and there are magnetic fields, the fields can constrain cross-field motion and channel the flow along field lines. This is how astrophysical jets from black holes and young stars maintain collimation over light years. But those systems have enormous magnetic fields generated by accretion disks or stellar dynamos. Comets don't have those field sources. Natural comets have weak or negligible magnetic fields, not strong enough, not organized enough, not capable of producing the degree of collimation we're seeing in 3I Atlas. You could invoke dust loading. If the gas is carrying a lot of solid particles, the momentum coupling between gas and dust can affect the dynamics. Heavy dust loading can suppress certain instabilities that would otherwise cause spreading, but this works at short ranges, close to the source where gas density is high and coupling is strong. At the distances we're talking about, hundreds of thousands of kilometers, the gas has become so tenuous that dust is essentially in ballistic flight. It's not coupled to the gas anymore. It's following its own trajectory based on the velocity it had when it decoupled, and ballistic particles spread. Their initial velocity distribution, however narrow, causes them to diverge over distance. The only way to maintain collimation over 400,000 kilometers is if the particles are all moving in very nearly parallel directions with very similar speeds. The velocity distribution has to be extraordinarily narrow, and achieving that through natural ejection processes is difficult to impossible. Natural processes create distributions, spreads, variations in velocity and angle that accumulate over distance to create the spreading we observe in normal jets. Getting a narrow velocity distribution requires either extremely controlled ejection conditions, which natural thermal processes don't provide, or some mechanism that focuses or selects particles after ejection, removing the ones that aren't moving in the preferred direction and allowing only the well-aligned ones to continue. And selection mechanisms don't exist in nature for this application. There's no natural filter that preferentially removes off-axis particles from a jet traveling through vacuum. But engineered systems can create narrow velocity distributions. Nozzles do this. Carefully designed throat and expansion geometries accelerate gas in specific directions and suppress crossflow. The result is exhaust that's highly directional, that maintains collimation far beyond what natural vents produce. Rocket engines achieve this. Ion thrusters achieve this. Any propulsion system designed to generate controlled thrust has to solve the collimation problem through engineering. So when you see a jet that's more collimated than natural processes can explain, you're looking at either unknown physics or known engineering. And known engineering becomes a simpler explanation than unknown physics when the unknown physics would require multiple new mechanisms all working together perfectly to produce the observed result. This is the razor's edge where the natural versus artificial debate balances. How many new assumptions are you willing to make to preserve the natural framework? At what point does adding mechanisms and special conditions become less parsimonious than accepting that the object might be designed? For most of the astronomical community, that point hasn't been reached. The default assumption remains natural origin, and the burden is on those claiming artificial to prove it definitively. But for researchers like Loeb, who are actually calculating probabilities rather than defending positions, the burden of proof is shifting. The natural explanation is accumulating so many required assumptions that its probability is decreasing, while the artificial explanation, despite starting with a very low prior, is increasing as each new piece of evidence that's hard to explain naturally emerges. The quasi-periodic variations add another dimension to this analysis. When you track how the anti-tail brightness changes over time, when you look for patterns in the variations, you find structure. Not random noise, not simple monotonic trends, but fluctuations that have characteristic timescales and that repeat with imperfect regularity. The dominant period is roughly 16 hours. That's close to estimates of 3I Atlas's rotation period based on overall brightness variations of the nucleus. So initially, researchers assumed the anti-tail variations were tied to rotation. As active regions on the surface rotate in and out of view, as solar illumination changes with rotation, you'd expect jet activity to vary on the rotation period. This is normal cometary behavior. But the details don't match perfectly. The phase of the variations, the timing of when the anti-tail brightens and dims, doesn't align cleanly with the rotation phase derived from nucleus photometry. There's an offset, a lag or lead that varies over time. And there are additional periodicities, shorter timescales, that don't correspond to rotation at all. Fluctuations on hour-long timescales, variations that look like pulsing or cycling rather than the smooth changes you'd expect from rotating active regions. These short-period variations are the ones that are hardest to explain naturally. Rotation is locked to the object's physical spin. You can't have brightness variations faster than rotation unless the source itself is turning on and off independent of the surface rotation. And what natural mechanism turns jet activity on and off on our timescales? Thermal processes operate on longer timescales. Heat conducting through ice, building up pressure, opening vents. These processes take time, hours to days typically, not sub-hour cycling. You could invoke pressure release events, subsurface pockets suddenly exposing and venting, but those are typically brief outbursts, not rhythmic oscillations. Resonant phenomena might create periodicity. If there are coupled oscillations in the comet's interior, feedback between heating and structural response, you might get rhythmic behavior. But resonances lock to characteristic frequencies determined by material properties and geometry. They're stable, consistent. The variations in 3I Atlas's antitail show period variation jitter, as if the pacing is coming from a process that isn't perfectly regular rather than from a physical resonance that should be stable. Systems with timers or control logic show exactly this kind of behavior. Quasi-periodic operation, where the cycle time varies slightly because the trigger conditions aren't perfectly repeatable or because there's noise in the control system. If the anti-tail is being driven by mechanisms that activate based on measured conditions, temperature or pressure or power availability, you'd expect variations around a nominal cycle time rather than perfect periodicity. This is speculation built on limited data. The periodicities are subtle enough that they could be artifacts of the analysis, could be noise being misinterpreted as signal, but multiple independent researchers using different analysis techniques are seeing similar patterns, are extracting similar characteristic timescales, are finding structure in the variations that's unlikely to be purely random. And when you combine the quasi-periodic behavior with the collimation problem and the particle size problem and the energy budget problem and all the other anomalies, the cumulative picture is of an object that operates rather than just responds, that shows active behaviors rather than passive ones, that exhibits characteristics you'd expect from systems executing programmed sequences rather than from ice responding to solar heating. None of this is proof, but it's evidence. It's observations that fit artificial hypothesis better than they fit natural explanations. And as evidence accumulates, as more pieces of the puzzle show this same pattern, the probability calculations shift. The question that hovers over all of this is why anyone would build something like 3I Atlas. If it is artificial, what's its purpose? What mission justifies sending an object through interstellar space on trajectories that take hundreds of thousands or millions of years? Human-designed space probes have missions measured in years or decades. Voyager is pushing 50 years, and it's considered an extraordinary achievement. The idea of designing something that operates for geologic timescales is outside our engineering experience. We don't build things that last millions of years. We don't create projects that won't yield results for timescales longer than civilizations typically endure. But a civilization that's stable over millions of years, a civilization that thinks on cosmic timescales, might approach exploration and communication differently, might send out probes knowing that the builders will be long dead before the probes reach their destinations, might create infrastructure designed to last for ages because that's how long it takes to study or communicate across galactic distances. If you're that kind of civilization, if your perspective extends across millions of years, then sending durable probes through stellar systems on ballistic trajectories makes sense. You're not expecting immediate results. You're creating a network that operates on timescales where light speed delays are negligible compared to mission duration. You're gathering data that will be analyzed by descendants so distant they're effectively a different civilization. And from that perspective, 3I Atlas's behavior is exactly what you'd expect, an object passing through our solar system, gathering data using whatever sensors it possesses, not attempting communication because we're not the intended audience or because it's operating in passive observation mode, just recording and continuing, executing a mission that was programmed millions of years ago and that will continue for millions of years more. This is deeply speculative. We have no evidence that such civilizations exist, no proof that anyone thinks on million-year timescales or operates interstellar probe networks. But if they do exist, if galaxy-spanning civilizations are operating infrastructure we're only now beginning to detect, then 3I Atlas is exactly what that infrastructure would look like. Not flashy, not communicative, not designed to impress primitive observers, just functional, durable, passing through and observing and continuing according to whatever protocols were established when it was built. The alternative is that we're projecting, that we're seeing patterns that aren't there because we want to find evidence of other intelligence, that the anomalies are real but natural, and that our failure to explain them reflects our limited understanding rather than the object's artificial origin. that we're like ancient humans seeing faces in clouds, creating meaning from randomness because our brains are wired to detect agency even where none exists. This is the skeptical position, and it's important to take seriously. The history of science is full of phenomena that seemed inexplicable, that violated known physics, that sparked speculation about new forces or unknown entities, and that eventually turned out to have conventional explanations once better data was gathered or better models were developed. Continental drift seemed impossible until plate tectonics was understood. Quasars seemed to violate energy conservation until we recognized they were powered by supermassive black holes. Pulsars were briefly called LGM for little green men, because their regular signals seemed too precise to be natural until we understood they were rotating neutron stars. Every time we encounter something we don't immediately understand, there's a temptation to invoke exotic explanations, and almost every time patience and better data lead to conventional explanations that fit within established frameworks. The track record suggests we should be very cautious about claiming anything is artificial or physics-breaking or requiring new fundamental understanding. But occasionally, the exotic explanation turns out to be correct. Occasionally, the phenomena that violated expectations really were new. Black holes were considered mathematical curiosities for decades before we accepted they physically existed. Dark matter seemed like an ad hoc fix to save gravity theories until the evidence became overwhelming. Quantum mechanics violated classical physics so thoroughly that even its pioneers were uncomfortable with the implications. Science progresses by taking anomalies seriously while maintaining skepticism, by investigating the unusual rigorously while not jumping to conclusions prematurely, by being open to revision while insisting on evidence. And with 3i Atlas, we're in that uncomfortable space where the anomalies are real and documented, but the explanations are uncertain and debated. The particle size calculation is as rigorous as these things get. The physics is straightforward. The observations are clear. Normal cometary dust doesn't work. That's not speculation. That's mathematics applied to measurements. And the implications of that fact are what we're grappling with. Either we're missing something about cometary physics, some process or mechanism that operates in interstellar objects, but not in solar system comets, and that mechanism explains the particle sizes and the collimation and the energy budget and all the other anomalies. Or we're looking at something that isn't a comet, something designed and built, something executing a mission we don't understand. The Jupiter encounter will provide data that might distinguish between these scenarios. We'll stress the object in ways that natural and artificial systems respond to differently. We'll create observation opportunities that aren't available during the Earth flyby, and the results, whatever they show, will either confirm or challenge our current understanding of what we're seeing. But there's a deeper question beneath all the technical analysis and probability calculations, a question about how we handle uncertainty and ambiguity when the stakes are this high. Because if there's even a 10% chance that 3i Atlas is artificial, if the probability is non-negligible, even if it's not dominant, shouldn't we be treating it as a potential first contact scenario? Shouldn't we be preparing for that possibility, even while continuing to investigate whether natural explanations might work? Or is it better to maintain the presumption of natural origin until it's definitively ruled out, to avoid the societal disruption and panic that might result from suggesting we're being visited, to trust that authorities will handle any genuine contact scenario appropriately behind the scenes while keeping the public calm through carefully managed messaging? These are policy questions, not just scientific ones, and different people will answer them differently based on their views about transparency versus security, about public capacity to handle disturbing information, about whether citizens have a right to know, or whether that right is superseded by the need to prevent panic. What's clear is that the decision is being made, has been made already in how data from the December flyby has been managed and released. And that decision will be tested at Jupiter when independent observation networks are watching and when centralized control of information becomes much harder to maintain. The distributed observation campaign for Jupiter is already more extensive than what occurred at Earth. More amateur astronomers are involved, more data sharing agreements are in place. More international coordination has been established. The observation network is robust enough that suppressing information would require coordinated censorship across dozens of countries and thousands of independent actors. Possible in principle, but difficult in practice. If something dramatic happens at Jupiter, if 3I Atlas maneuvers or transmits or survives tidal stress in ways that clearly indicate artificial origin, that information will leak even if official channels try to suppress it. And once it leaks, once it's distributed globally through independent networks, the narrative control fails and the truth, whatever it is, becomes public knowledge, whether authorities are ready for that or not. This is the inflection point we're approaching, not just in understanding what 3I Atlas is, but in how humanity handles information about potential extraterrestrial contact. Do we maintain the traditional gatekeeping model where authorities decide what the public can know? Or do we embrace transparency and distributed verification and accept that some information is too important to be controlled? The answer will emerge from how the Jupiter encounter is handled, from whether data is released openly or restricted, from whether independent observations are acknowledged or dismissed, from whether the scientific process operates as it's supposed to or gets overridden by security concerns.
And beneath all of this, the particle size problem persists. The mathematical proof that what we're seeing doesn't fit natural models. The quantitative evidence that 3I Atlas is breaking physics as we understand it. The foundation on which all the speculation and analysis and debate rests. The particles are too large. The collimation is too tight. The energy budget doesn't balance. The direction is wrong. The variations are structured. And the cumulative probability that all of these anomalies result from natural processes we don't understand is decreasing, while the probability that we're looking at something designed is increasing, not to certainty, not to the point where we can definitively claim artificial origin, but to levels where dismissing the possibility becomes harder to justify than taking it seriously, where the burden of proof has shifted enough that natural hypothesis advocates need to provide mechanisms, not just assert that such mechanisms must exist. We're in the gap between what we know and what we believe, between what the data shows and what our frameworks predict, between observations that violate expectations and explanations that stretch credibility. And Jupiter is the event that might close that gap or widen it further depending on what the observations reveal. The countdown continues. Days are passing. The object speeds toward the encounter. The instruments are calibrated. The observation schedules are finalized. And soon, very soon, we'll have new data that might resolve ambiguities or create new ones. That might answer questions or raise deeper ones. That might confirm we're looking at an exotic but natural comet or reveal that we're facing something far more profound. The particle size problem frames everything. Because if normal physics doesn't explain those particles, normal explanations don't explain the object. And if normal explanations fail, we're forced to consider what abnormal explanations might succeed. Forced to ask whether artificial is still extraordinary when natural requires stacking so many special cases that it becomes more exotic than the alternative. That's the question Jupiter will help answer. That's what we're waiting for as 3I Atlas approaches, and as the observation campaigns prepare. That's why this matters, and why the particle size calculation, the physics-breaking mathematics showing that conventional dust doesn't work, is the key that might unlock the biggest mystery we've encountered. The anti-tail exists, stretches across 400,000 kilometers, points toward the sun when it should point away, contains particles that shouldn't be there, shows collimation that shouldn't persist, varies on timescales that don't match rotation, and resists explanation through standard cometary physics no matter how many exotic conditions you invoke. It's real. It's measured. It's documented in peer-reviewed analysis based on observations anyone can verify, and it's forcing us to confront the possibility that our understanding is incomplete or that what we're observing isn't natural. Either answer is revolutionary. Either we're learning that comets can be far stranger than our theories predicted, which expands our understanding of planetary formation and composition across diverse stellar environments. Or we're confirming that intelligence exists beyond Earth and operates on scales and timescales we're only beginning to detect. The implications cascade from that simple binary. If natural, we rewrite textbooks and redesign models and acknowledge that decades of cometary research missed crucial phenomena. If artificial, we rewrite our understanding of humanity's place in the cosmos and prepare for a future where we're not alone and where visitors might be here already. Jupiter decides. Or at least, Jupiter provides the data that might let us decide with higher confidence than we currently possess. The encounter is the test, the stress, the observation opportunity that doesn't repeat. Our one chance to see how the object responds to the most extreme environment it will encounter in our solar system, and the world watches, some eagerly, some anxiously, some skeptically. But watches nonetheless because whatever the answer turns out to be, it matters. Matters for science, matters for philosophy, matters for how we understand ourselves and our cosmic context. The particle size problem is the foundation. The collimation is the structure. The energy budget is the constraint. The quasi-periodic variations are the hint. And Jupiter is the test that might bring it all together or tear it all apart. The object continues. The observations accumulate. The analysis deepens. And the question persists, refusing to be answered prematurely, but demanding to be taken seriously. What is 3I Atlas? What physics can explain it? What explanations remain standing when the implausible ones are eliminated? And what does the answer mean for everything we thought we knew about comets, about interstellar visitors, about our isolation or our embeddedness in a galaxy far more active than we imagined? The mathematics says normal dust doesn't work. The observations say collimation exceeds natural limits. The energy calculations say the budget doesn't balance, and the cumulative evidence says something unusual is occurring that demands explanation beyond dismissive assertions, that natural processes must somehow account for it. We're past the point where ignoring the anomalies is defensible, past the point where invoking unknown mechanisms without specifying them constitutes explanation. Past the point where maintaining comfortable assumptions takes priority over following the data wherever it leads. The data leads to discomfort, to questions we're not ready for, to possibilities that challenge frameworks we rely on. But the data is what it is. The particle sizes are what they are. The antitail exists as observed. And the physics that should govern these phenomena apparently doesn't. So we're left with the question that won't go away no matter how much we'd prefer simpler answers. Are we witnessing nature being stranger than expected, or are we encountering technology from beyond? Are the anomalies telling us we need better models, or are they telling us we need to expand our search for intelligence to include objects that pass through rather than signals we receive? Jupiter approaches. The answer, partial or complete, is coming. And the particle size calculation, the mathematical proof that normal cometary physics breaks when applied to 3I Atlas, remains the foundation on which everything else is built. Breaking physics, demanding answers, forcing questions we can't avoid no matter how uncomfortable they make us, and counting down to the moment when stress and observation and analysis converge to reveal what's actually passing through our solar system and what it means for everything we thought we understood. The Jupiter trajectory itself contains information that's often overlooked in discussions focused on the antitail and particle physics, because the path 3I Atlas is following, the specific approach angle and distance and timing, is not random, it's precise. Precisely enough that if you're looking for evidence of control versus chaos, the trajectory deserves the same scrutiny we're applying to the material ejection. Interstellar objects entering the solar system can arrive from any direction with any velocity within the range of galactic kinematics. The distribution should be essentially random, sampling the velocity distribution of objects in the local galactic neighborhood. Some come fast, some come slow, some dive deep into the inner solar system, some barely graze the outer edges. The trajectories are determined by initial conditions at entry, millions of years of travel through interstellar space, and the gravitational influence of the Sun once the object enters the solar system's sphere of influence. For any given object, the probability of passing close to a specific planet is low. Space is vast. Planets are small. The cross-section for a close encounter, the effective target size, is tiny relative to the volume of the solar system. Most interstellar visitors pass through without coming particularly close to any planet. They might cross the orbital planes, might pass within the orbit of Jupiter or Neptune, but actual close approaches, distances measured in tens of millions of kilometers rather than billions, are uncommon. 3I Atlas is doing multiple close approaches. Earth in December, Jupiter in January. That's not impossible. The trajectory could be coincidentally aligned to pass near both planets. But the probability is low, and when you combine low probability trajectory with low probability physical behavior, the cumulative improbability starts to become significant. The approach to Jupiter is particularly interesting because of the distance. 52 million kilometers. That's close enough to experience substantial gravitational deflection, close enough that Jupiter's gravity will significantly alter the trajectory, close enough to use the planet as a gravity assist, gaining velocity from the encounter and being flung outward faster than the object would travel without the assist. Gravity assists are standard techniques in mission planning. Every deep space probe uses them. Voyager used Jupiter and Saturn. New Horizons used Jupiter. The technique is well understood. You approach a massive planet on a specific trajectory, and the planet's gravity bends your path and changes your velocity in predictable ways. Depending on the geometry, you can gain or lose speed, change direction, reshape your orbit. For 3I Atlas, the Jupiter encounter will increase its velocity, will accelerate it outward, will give it additional kinetic energy that comes from Jupiter's orbital motion. The planet is moving around the Sun, carrying enormous momentum. When the comet passes close, it steals a tiny fraction of that momentum, gaining speed while Jupiter loses an utterly negligible amount. The result is that 3I Atlas exits the solar system faster than it would have without the Jupiter encounter. If you were designing a mission, if you wanted to visit the inner solar system and then leave quickly, you'd plan exactly this kind of trajectory. Approach from above the ecliptic plane, allowing a steep dive down to perihelion. Pass near Earth during the approach, providing observation opportunities, then swing out toward Jupiter, using the giant planet's gravity to boost your departure velocity. It's efficient. It's elegant. It's exactly how a mission planner would route a probe through the solar system if the goal was to observe Earth and then exit rapidly. The natural explanation is that this is coincidence, that the trajectory just happens to be aligned this way, that the millions of years of interstellar travel and the gravitational perturbations along the way, and the initial conditions at ejection from whatever stellar system the object came from, all combined to produce entry conditions that result in this specific path. It's possible, unlikely, but possible. Trajectories are deterministic once initial conditions are set, and those initial conditions are random, so any specific trajectory has low probability, but some trajectory must occur. But when you're already dealing with physical anomalies, when you already have particle size problems and energy budget problems and collimation problems, adding trajectory precision to the list makes the cumulative case stronger. Each individual feature might be explicable through special circumstances. But the combination, the fact that multiple independent features all happen to align in ways that look designed, shifts the probability calculus. This is Bayesian updating in action. You start with a prior probability, your initial estimate before examining evidence. For artificial origin, most researchers start with a very low prior, maybe 1 in a million or 1 in a billion, because the vast majority of objects should be natural. Then you update based on evidence. Each piece of evidence that's more consistent with artificial than natural increases the posterior probability. And if you accumulate enough evidence, even starting from a very low prior, the posterior can become substantial. The problem is that different researchers assign different likelihoods to the evidence. How much more consistent with artificial is the particle size distribution? How improbable is the trajectory precision? How unlikely is the collimation? These are judgment calls. Different analysts will have different assessments, and those differences in likelihood assignment lead to different posterior probabilities, even when everyone is using the same mathematical framework. Loeb's 40% estimate reflects his likelihood assessments. Other researchers who are more conservative in their assignments, who think natural explanations are more probable even for anomalous observations, arrive at lower posteriors. Maybe 1% or 5% or 10%, but still non-negligible. And a few researchers, those most skeptical of artificial possibilities, assign likelihoods that keep the posterior extremely low even after updating on all the evidence. There's no objective way to resolve these differences without more data. The Jupiter encounter provides that data, provides observations that might have very different likelihoods under natural versus artificial hypotheses. And those observations will cause everyone's probability estimates to update, hopefully converging toward a consensus as the evidence becomes less ambiguous. But the trajectory precision is data we have now, not as ambiguous as some other features, not subject to as much interpretation. The path is measured, the geometry is calculated, and the fact that it threads past both Earth and Jupiter with close approaches to both is quantifiable and unlikely and worthy of consideration in any honest probability assessment. The energy considerations at Jupiter add another layer to the analysis. Because the tidal forces aren't just mechanical stress, they're also energy input. When Jupiter's gravity pulls on different parts of the object with different strengths because those parts are at different distances from the planet, that differential gravitational force creates tides, and tides heat material through friction and deformation. This is how Io, Jupiter's innermost large moon, stays volcanically active. The tidal forces from Jupiter constantly squeeze and flex Io's interior, generating heat through friction, keeping the interior molten despite the moon's small size. Tidal heating is a powerful energy source in the right circumstances. For 3I Atlas, passing at 52 million kilometers, the tidal forces are much weaker than what Io experiences in its tight orbit, but they're not zero. And if the object has the right internal structure, if there are regions that can deform and generate frictional heating, tidal energy input during the Jupiter encounter could be significant. This could trigger outgassing, could fracture frozen material and expose fresh volatiles, could create activity levels that seem inconsistent with solar heating alone because they're not powered by solar heating but by tidal energy. And if we see activity spikes during the Jupiter passage, activity that correlates with closest approach when tidal forces peak, that would support the natural explanation by providing an energy source we can quantify. But tidal heating also depends on internal structure, requires deformable material, requires dissipation mechanisms that convert mechanical stress into heat. If the object is a solid monolith, if it's structurally rigid and doesn't deform significantly under tidal stress, the heating will be minimal. And minimal heating means any activity increase can't be attributed to tides and must come from some other source. So the response to tidal stress becomes another test, another observation that distinguishes between scenarios. Rubble piles deform easily and heat substantially. Solid bodies resist deformation and heat minimally. Observing how much 3I Atlas deforms, measuring whether there's heating, tracking whether activity changes correlate with tidal force variations, all of these provide information about internal structure and composition. And internal structure matters for the artificial hypothesis because designed objects have different structural properties than natural aggregates. If you're building a probe intended to survive interstellar travel and gravitational encounters with planets, you design for structural integrity. You use materials that resist stress. You create internal supports and framework that maintain shape under load. You don't build rubble piles, you build coherent structures. So, if 3I Atlas responds to Jupiter's tidal stress like a solid body rather than like a rubble pile, that's evidence consistent with design, not proof. Natural objects can be monolithic too, especially small ones where self-gravity is weak and material strength can dominate. But combined with all the other evidence, structural integrity adds to the artificial column of the probability ledger. The timing of the encounter is also worth noting. January 2026, just weeks after the closest approach to Earth. The object is moving outward, receding from the Sun. Activity should be decreasing as solar heating diminishes. But the Jupiter encounter might cause activity changes that override the solar distance trend, might create emissions or outgassing or structural responses that wouldn't occur if the object were just coasting through empty space. This creates an observational window, a period when the object is doing something, responding to environmental changes, potentially revealing characteristics that aren't visible during quiet phases, and that window is being prepared for more thoroughly than any previous interstellar object observation campaign. The James Webb Space Telescope is the flagship instrument, but it's far from the only asset being tasked. Ground-based observatories across the globe are scheduling observations. Radio telescopes are preparing to listen for electromagnetic emissions. X-ray telescopes are planning exposures to search for high-energy signatures. And critically, the amateur network is organizing a distributed observation campaign that will involve thousands of telescopes simultaneously monitoring the object during the encounter period. This is unprecedented. No previous interstellar visitor has received this level of coordinated attention. Oumuamua was gone before we really understood what we were seeing. 2I Borisov was studied extensively, but it behaved like a normal comet and didn't trigger the kind of intense scrutiny that 3I Atlas is receiving. This time, we're prepared. This time we have the instruments and the coordination and the motivation to capture everything we possibly can during the limited observation window. And the data will be analyzed in real time. Processing pipelines are being established to handle the data flow and produce preliminary results within hours of observation. Automated systems will look for transients, for sudden changes, for any behavior that deviates from predictions. Human analysts will examine the processed data and make decisions about follow-up observations. The whole operation is designed to be responsive, to adapt to what's being seen rather than just executing a pre-planned sequence. This flexibility is important because we don't know what to expect. The models make predictions, but the models have been wrong before. 3I Atlas has repeatedly defied expectations. The anti-tail wasn't predicted. The particle sizes weren't expected. The trajectory precision wasn't anticipated. So assuming Jupiter will be routine, that the observations will be boring, would be naive. Better to prepare for surprises, to have the capability to respond quickly when unexpected phenomena appear. And if something truly dramatic happens, if the object maneuvers or transmits or does anything that's unambiguously artificial, the response protocols are in place. Not publicly documented protocols, not official government procedures, but informal agreements among researchers, among amateur networks, among independent observers about how to handle and verify and distribute information that might be historically significant. The agreements emphasize verification, require multiple independent confirmations before claiming anything extraordinary. Mandate data sharing so that others can check the analysis and ensure there aren't errors or artifacts being misinterpreted as signal. Prioritize transparency over speed, preferring to be right over being first. But they also emphasize distribution. If something significant is detected, if there's genuine evidence of artificial behavior, that information gets shared broadly and quickly, gets posted to multiple platforms simultaneously, gets distributed through channels that can't be easily censored or controlled. The goal is to make suppression impossible through redundancy and speed. This might seem paranoid, but it's based on what happened after the December Earth flyby. The data gaps, the missing observations, the coordinated narrative shift, the sudden silence from researchers who were previously vocal. All of these created suspicion that information is being controlled, that transparency is being sacrificed to manage public perception or to prevent panic, or for reasons that aren't being publicly stated. The Jupiter Observation Network is designed to be robust against that kind of control, is designed to operate outside the official channels that can be restricted, is designed to ensure that whatever is observed becomes public knowledge whether authorities want it to or not. This might be unnecessary. The control might have been coincidental rather than coordinated. The data gaps might have mundane explanations. The silence might reflect appropriate scientific caution rather than suppression. But whether necessary or not, the Distributed Observation Network provides insurance, ensures that if Jupiter reveals something important, that revelation reaches the public rather than being buried in classified reports. The philosophical dimension of all this deserves explicit acknowledgement, because what we're really grappling with isn't just whether 3I Atlas is natural or artificial. It's how we handle profound uncertainty about questions that matter deeply. How we balance the need for careful analysis against the possibility that delay means missing critical insights. How we weigh the risk of claiming artificial origin prematurely against the risk of dismissing it too quickly. Different worldviews lead to different approaches. If you believe the universe is likely populated, if your prior probability for intelligence existing beyond Earth is high, then you'll interpret ambiguous evidence more favorably toward artificial explanations. If you believe intelligence is rare, if you think Earth might be unusual or unique, then you'll require stronger evidence before accepting that an interstellar visitor is technology. Neither position is inherently wrong. They're based on different assumptions about fundamental questions we can't currently answer. How common is life? How often does intelligence evolve? How long do technological civilizations last? We don't know. We have one data point, Earth, and generalizing from one example is impossible. So we're left with beliefs rather than knowledge. Informed beliefs based on what we understand about planetary formation and biological evolution and the history of life on Earth. But beliefs nonetheless, and those beliefs color how we interpret observations of 3I Atlas. The particle size problem exists independent of belief. The measurements are what they are. The calculations are reproducible. But the interpretation, whether this means exotic natural processes or artificial jets, depends on unstated assumptions about what's possible and what's probable. Making those assumptions explicit would help the debate, would allow people to see where disagreements actually originate, would clarify that often we're not arguing about data, but about priors, about fundamental beliefs that shape how we process evidence, and it would highlight that both positions contain risk. Claiming artificial too quickly risks credibility, risks crying wolf, risks making future claims less believable. But dismissing artificial too quickly risks missing first contact, risks failing to prepare for a discovery that would be the most important in human history, risks being so attached to comfortable explanations that we ignore evidence pointing elsewhere. The conservative approach, waiting for definitive proof before entertaining extraordinary hypotheses, minimizes the first risk but maximizes the second. The bold approach, taking seriously the possibility of artificial origin based on accumulating anomalies, does the reverse. And there's no objectively correct balance. Different people will reasonably choose different points along that spectrum. What's important is that the choice is being made consciously, that researchers are aware of the trade-offs, that the community isn't dismissing artificial possibilities reflexively without examining the evidence, but also isn't jumping to conclusions based on ambiguous data that could be explained multiple ways. With 3I Atlas, we're seeing both extremes. Some researchers are willing to assign 40% probability to artificial origin based on current evidence. Others maintain that probability is effectively zero despite the anomalies. And most fall somewhere in between, acknowledging the observations are unusual while remaining skeptical that artificial is the correct explanation. The Jupiter encounter will move everyone's estimates, will provide data that updates probabilities in whatever direction the evidence points. And critically, that update will happen simultaneously across the global research community because the observations are being made by distributed networks rather than centralized institutions. This democratization of data collection is new. Previous major astronomical discoveries were made by large telescopes at professional observatories. The data flowed through established channels. Analysis was done by credentialed researchers. Results were published in peer-reviewed journals after months of review. The process was controlled and orderly and slow. But amateur astronomers now have access to equipment that would have been professional grade a decade ago, have software that can process images and extract photometry and perform analysis that previously required specialized training, have communication networks that allow instant sharing of observations and collaborative analysis across borders and institutions.
The result is that major discoveries increasingly come from distributed amateur networks rather than from big observatories. Supernovae are discovered by amateurs. Exoplanet transits are confirmed by amateurs. Asteroid tracking is substantially performed by amateurs. And now, the observation campaign for 3I Atlas at Jupiter involves more amateur participation than professional. This changes the dynamics of information control. You can't classify data that's being collected by thousands of independent observers, can't restrict access to observations that are being shared openly on forums and social media, can't manage the narrative when the narrative is being written collectively by a distributed community. And that's probably healthy for science, even if it's uncomfortable for authorities used to controlling sensitive information. Because science is supposed to be open, data is supposed to be public. Results are supposed to be reproducible by anyone with the appropriate tools. The traditional model where large institutions controlled access to observations was never ideal, even if it was necessary given the technology limitations. Now, those limitations are gone. Equipment is affordable, software is free, communication is instant, and the model is shifting toward distributed observation and collaborative analysis, whether institutions are ready for that shift or not. 3I Atlas is a test case for this new model, for whether distributed networks can do serious science, for whether amateur contributions can be rigorous enough to be trusted, for whether coordination can happen without centralized control. And so far, the test is going well. The observation plans are solid, the data quality is good, the analysis is being performed carefully with appropriate skepticism and verification. If Jupiter reveals something important, if the observations show clear evidence of artificial behavior or definitively rule it out, that discovery will be made by the network, will emerge from collaborative analysis of data collected by hundreds of independent observers, will be verified through redundant observation and cross-checking rather than through institutional authority. And that's how it should work. That's how science works best. Through distributed effort and collective verification and open debate, not through gatekeeping and information control and authority-based claims. The particle size problem that started this investigation is being addressed the same way, multiple independent analyses using different methods all arriving at similar conclusions. The data is public, the calculations are reproducible. Anyone who doubts the results can examine the observations themselves and verify that yes, the particles are larger than normal cometary dust, and yes, this creates problems for natural explanations. That's science working properly. That's how knowledge advances, through transparent analysis of publicly available data leading to conclusions that others can verify or challenge, not through assertions that must be accepted on faith because the underlying data is classified or restricted. The particle size problem that started this investigation is being addressed the same way. Multiple independent analyses using different methods all arriving at similar conclusions. The data is public. The calculations are reproducible. Anyone who doubts the results can examine the observations themselves and verify that yes, the particles are larger than normal cometary dust, and yes, this creates problems for natural explanations. That's science working properly. That's how knowledge advances, through transparent analysis of publicly available data leading to conclusions that others can verify or challenge. not through assertions that must be accepted on faith because the underlying data is classified or restricted. As Jupiter approaches, as the observation window opens, we'll see whether the new distributed model can handle a discovery of profound importance, whether the verification processes are robust enough to distinguish genuine anomalies from artifacts and errors, whether the community can maintain appropriate skepticism while remaining open to extraordinary possibilities. The stakes are high. If 3I Atlas is artificial, if the Jupiter observations confirm that, the impact on human civilization is difficult to overstate. It's not just an astronomical discovery, it's confirmation that we're not alone, that intelligence exists beyond Earth, that the galaxy is populated and that visitors pass through our solar system whether we notice them or not. That knowledge changes everything, changes how we think about our future, about whether space exploration is about claiming empty territory or about encountering neighbors, about whether we're pioneers or latecomers, about what threats and opportunities exist beyond our planet. It changes philosophy, changes religion for many people, changes the fundamental questions about meaning and purpose and humanity's significance. If we're one civilization among many, if intelligence is common, the existential questions that have occupied human thought for millennia take on different dimensions. And it changes policy, changes how we think about space security and planetary defense, and whether our concerns should focus on asteroids and comets, or whether we need to prepare for the possibility of encounters with technology from beyond. Changes whether SETI should be passive listening or active transmission. Changes whether we should be announcing our presence or remaining quiet. These are enormous changes, the kind that reshape civilizations. The kind that people resist because change on that scale is frightening regardless of whether the implications are positive or negative, and that resistance is part of why information control seems attractive to authorities, why managing the narrative seems like prudent policy rather than censorship. But the distributed observation network makes that control impossible, makes resistance futile. The truth will emerge because too many people are watching and too many channels exist for distributing what they see. The only question is whether the emergence is orderly through official channels that maintain credibility, or chaotic through leaks and unofficial revelations that undermine institutional authority. Better to embrace transparency, to release data as it's collected, to trust that people can handle disturbing information if it's presented honestly and carefully, to recognize that the brief period when information could be effectively controlled has ended and that the new reality is distributed verification and collaborative sense-making. The Jupiter encounter will test this, will show whether institutions can adapt to the new model or whether they'll cling to outdated approaches that no longer work. Will demonstrate whether transparency or control wins when they come into conflict. Will reveal whether the future of major discoveries is institutional or distributed. And beneath all of this, the object continues, speeds toward Jupiter, approaches the encounter that will test it and test our theories and test our ability to handle whatever the observations reveal, breaking physics with its particle sizes, defying models with its collimation, challenging expectations with its trajectory, operating or drifting, we're not sure which, but certainly doing something unusual enough to demand explanation. The anti-tail stretches, 400,000 kilometers of material that shouldn't exist, pointing in a direction it shouldn't point, composed of particles larger than natural processes should eject, a structure that persists when it should disperse, that maintains collimation when it should spread, that varies quasi-periodically when it should fluctuate randomly or cycle with rotation. Every feature is a question, every measurement is a challenge. Every observation adds to the cumulative case that something unusual is happening that doesn't fit comfortable categories and that demands either expanding those categories or creating new ones. And the expansion or creation happens at Jupiter, where stress and observation combine, where natural and artificial predictions diverge most clearly, where ambiguity might finally resolve into understanding. The countdown is measured in days now. Single-digit days until closest approach. until the observation window opens fully, until the data starts flowing that will answer questions or raise new ones, or most likely both simultaneously. The instruments are ready. The networks are coordinated. The analysis pipelines are tested. Everything that can be prepared has been prepared. Now we wait for the object to arrive, for nature or technology to reveal itself through response to tidal stress and electromagnetic environment and observational geometry. The particle size calculation stands regardless of what Jupiter shows. The mathematics is sound, the measurements are accurate. Normal cometary dust doesn't explain the anti-tail. That's established. Whether the explanation is exotic natural processes or artificial design remains to be determined, but the conventional explanation is ruled out. That's the foundation, the solid ground on which analysis rests, the quantitative proof that 3I Atlas breaks the rules we thought governed these objects. And breaking rules demands explanation, whether the explanation is comfortable or not. Jupiter will constrain the possibilities, will eliminate some hypotheses and strengthen others, will move us closer to understanding what's passing through our solar system and what it means. And the world watches, some with hope, some with fear, some with skepticism, but watches nonetheless because the answer matters. Because whether we're witnessing nature's creativity or technology's presence, we're seeing something rare and important and potentially transformative. The anti-tail glows in images, points sunward, stretches impossibly far, maintains impossible collimation, contains impossible particles, and challenges us to explain it without resorting to impossibilities ourselves. The object speeds on, indifferent to our confusion. Following physics or programming, we'll soon discover which. Approaching the test that might finally tell us whether we're alone or observed, whether the galaxy is empty or active, whether the future is ours to explore or is already occupied by civilizations that sent this visitor millions of years ago. Days remaining. The encounter approaches, the data collection begins, and the particle size problem, the physics-breaking evidence that started this investigation, awaits confirmation or refutation or deeper mystery from observations that will either solve the puzzle or scatter the pieces further. Breaking physics, demanding answers, forcing questions we can't avoid, and counting down to the moment when Jupiter's gravity and humanity's instruments combine to reveal what's real beneath the ambiguity and what truth emerges from the data when we finally look carefully enough to see it. The mystery persists, the object continues, and the answer, whatever form it takes, is approaching faster than we're prepared to comprehend it. But prepared or not, ready or not, comfortable or not, the truth is coming. And the particle size calculation says that truth will be strange regardless of which category it falls into. Natural but exotic, or artificial and profound. Either way, different from what we expected. Either way, expanding what we thought possible. Either way, breaking the comfortable assumptions that let us pretend the cosmos operates on human scales and follows human intuitions. 3I Atlas is teaching us otherwise, is showing us the universe is stranger and possibly more populated than our theories predicted, is forcing growth through discomfort and understanding through mystery. And Jupiter is where the lesson continues, where the next chapter unfolds, where the particle size problem meets gravitational stress and reveals whether physics breaks because our physics is incomplete or because what we're observing isn't governed by physics alone. The answer awaits, the object approaches, and we watch with instruments and hope and trepidation as the cosmic visitor that breaks our rules speeds toward the encounter that might explain why.